In this video, I will introduce the standard error and confidence interval. In a research study, we generally start by taking a sample from a population. We can then describe the distribution of a variable from our sample. For example, say that our variable's distribution has a mean of 6. Typically, we only take one sample of our underlying population and conduct our research study using this sample. But this is one place where statistics starts to get a little bit wacky. Say that instead of stopping after one sample from our population, we start from scratch and take a second sample. Since we're not including everybody from our population in our samples, each sample is going to have a slightly different distribution for our variable of interest. For example, say that in our second sample we get a mean of 6.5 instead of 6. Then we start from scratch again and take a third sample and get a mean of 5.5. If we do this over and over again, we would end up with a distribution of means from our samples. The means of our samples would most frequently cluster around our population mean, but sometimes we would just by chance get a sample with a mean that was way off from our population mean. Over time, the distribution of our means would follow a normal distribution. Our distribution of means would have its own mean and its own standard deviation, representing the average distance of our sample means from the mean of our sample means. I told you things were going to get a little bit wacky. Now let's take one step back into the land of hypothetical statistics. Again, this image shows our distribution of means from all of the samples we took from the population. Remember, we know that if our data are normally distributed, about 95% of our values fall within 2 standard deviations of the mean. These are the basic tenets of something in statistics called the central limit theorem. Luckily, we do not need to take an infinite number of samples from our population to estimate our standard error. Let's go back to reality, where we're taking a single sample from our population, then estimating the distribution of a variable from that sample. We can obtain an estimate of the standard error by dividing our sample's standard deviation by the square root of the sample size. Now let's take one step back into hypothetical statistics land. Again, this image shows our distribution of means from all of the samples we took from the population. Remember, we know that if our data are normally distributed, about 95% of our values fall within 2 standard deviations of the mean. The real number is actually about 1.96 standard deviations. Now remember, the standard deviation of this distribution of means from all of our samples is what we call the standard error. So when we're considering this distribution of means, we can say that 95% of our sample means fall within approximately 2 standard errors above or below the mean. This is how we get what is called the 95% confidence interval. We take our sample mean, then add and subtract approximately 2 standard errors. Graphically, when we're considering our distribution of means, the 95% at the bottom here is what we are referring to as our 95% confidence interval. Let's work through an example. Again, go back to the real world where we're taking a single sample from our population. We get a mean of 6 for the distribution of some variable. Then let's say the distribution has a standard deviation of 4 and we have 100 people in our sample. To estimate the standard error, or the standard deviation of our hypothetical distribution of means, we simply divide our standard deviation by the square root of our sample size. In this case, we divide 4 by the square root of 100 to get 0.4. To calculate our 95% confidence interval, we then take our mean and add or subtract approximately 2 standard errors. So in this case, we get a 95% confidence interval of 5.22 to 6.88. The interpretation of the confidence interval is a little bit weird. If we took an infinite number of samples of our population, the mean would fall in this range 95% of the time. This gives us an estimate of the accuracy of our mean. If we have a really wide 95% confidence interval around our mean, we're not very confident that our mean is accurate. If we have a very narrow 95% confidence interval around our In our example, we estimated the 95% confidence interval. This is the type of confidence interval most commonly reported in research. But there's no good reason we couldn't calculate a 99% confidence interval, or a 50% confidence interval, or any other confidence interval we're interested in. Notice, though, that as the percent of the confidence interval decreases, so does its width. As an extreme example, we're 100% confident that our population mean falls between negative infinity and positive infinity. We're 0% confident that our population mean is exactly our sample mean.